All right, class, hello. So we have left off having conquered the Ising model with both a really novel and interesting analytical approach through a normalization group, which really extracted the basic physics of critical phenomena in that a system at its critical point is scale invariant, and figured out a way to actually implement that notion mathematically in a scaling out and a self-similarity expression, which gave rise to us actually being able to, with pretty reasonable fidelity, compute those critical exponents we've spent so much of our past month talking about. That is still there is still some approximations invoked in such a scheme, and we relaxed those all entirely by putting the Ising model on a computer and actually studying it with a Monte Carlo algorithm that we first derived and then coded up last week. That really concludes our discussion of the Ising model in critical points, notions of second order phase transitions. So for the remainder of the course, what we're going to do is to apply some of those insights we gained along the way in terms of how we approach systems with interactions approximately, and apply those to a state of matter that we've largely neglected over the course of this semester, which is actually confronting liquids. So we're going to sketch out the basics of a theory of the liquid state over the course of the next few lectures, culminating essentially in an approximate equation of state for a fluid, van der Waals equation. And that will really be it. So we have 3 lectures to go, and so let's go ahead and begin this little last part of our journey. So before we get into new material, let's kind of put this in context. As we've said, we've spent a long time considering liquid vapor phase transitions. And that was interesting because we learned that liquid vapor phase transitions are the same thing as demixing transitions of your favorite multi-component system, or the same thing as how a magnet becomes demagnetized. And essentially, the discussion of that situation can be essentially codified in a phase diagram, say in the temperature density plane, where we have drawn many times that phase diagram looks something like this. At low density, we have a vapor. At high density, we have a liquid. And the distinction between the liquid and the vapor, where the coexistence between those 2 phases end, denotes the location of a critical point. We haven't drawn the pressure temperature phase diagram all that much, but you know what that would look like. There would be a line emanating or ending in a critical point that separates at low pressure and high temperature, a vapor phase, from the liquid phase at higher pressure and lower temperature. What we have largely neglected is that there is typically much more to the phase diagram of even a simple system. There is, at higher density, the possibility to crystallize, to form a crystal. And there's a region of coexistence that a liquid and a crystal could undergo. That region of coexistence is smushed into a line in the pressure temperature phase diagram, separating liquids from crystals. And indeed, there could be a region at really low temperature of vapor crystal coexistence, which is smushed into a line here. So a typical phase diagram, even of a very simple system, would have three phases: a liquid, a vapor, which we've talked quite a lot about, and a crystal. We've said next to nothing about vapor crystal coexistence or liquid crystal coexistence. What would be a way to describe such a transition? So we have indicated that the density is a good order parameter for a liquid vapor transition. A liquid vapor transition is a Z2 symmetry breaking, a particle hole symmetry breaking. The density essentially reflects that particle hole symmetry. What would be the analogous order parameter? What would be the number I would need to tell you in order to differentiate, say, a liquid from a solid, or to act as an order parameter for the liquid solid transition? So, as denoted in this phase diagram, most systems will change their density as they freeze. If they take a liquid to a solid, say a simple isotropic fluid like methane or argon will have an increase in its density as it freezes. But we know counter examples to that. Water will decrease its density when it freezes. So the density is not something that uniquely differentiates a liquid from a solid. To construct an order parameter, we could envision a box that is either in a liquid or crystal state. An order parameter would be a number that I would measure, a property of the system that I would measure, and uniquely be able to determine if that system is a liquid or a solid, irrespective of what it might be made out of. So how do you know if something is crystalline experimentally? What would you do? Well, some of you might be thinking that you would shine light on it. You know that crystals diffract light in a very particular way compared to liquids. That is a reflection of imagining what would happen if I, say, lined up this liquid or crystal in this box and picked out a slab, say, of width delta x, an area A, three-dimensional box, has some depth to it. I could define a density, which is not the bulk density, but the density in that little region of X. Say per number of particles per unit volume along X. Now, if I was to ask on average, what is the density as a function of x? I would get something very different for a liquid than I would for a crystal. For a liquid, the density is going to be uniform. The density for a liquid is the same everywhere in space, whereas for a crystal, the fact that it reflects light is manifesting the idea that there are specific planes where there are particles and otherwise there is free space. And the separation between those planes is the lattice spacing, some constant A. So a reasonable order parameter for a liquid crystal transition is not so much the average number density in a whole box, but rather how the particles are arranged in space. What is the density? How is the density spatially modulated? That's really what differentiates a liquid from a crystal. And precisely, a crystal is going to lack translational and also rotational symmetry. There are specific points in space which are special and have particles coincident with lattice planes, and there are specific points in space where there's none. The answer depends on where I look, which means that it's not translationally symmetric. A liquid, by contrast, is. Every direction I look at, on average, the system is the same. And in the context of the density, would just be the bulk density on average. So if we wanted to, we could develop a theory based on the spontaneous symmetry breaking associated with translations and therefore describe a crystallization transition. Such a theory would develop much like we did for the Ising model. We would write down probably the simplest model capable of spontaneously breaking translational symmetry and try to solve it approximately through the variety of techniques we've introduced. We are not going to do this. That's really the stuff of 220B, at least the latter portions of it, where we introduce something called the Landau-Ginzburg theory, which talks about or is equipped to handle spontaneous, continuous symmetry breaking. With such a theory, you can learn, for example, why there is no endpoint to a liquid crystal phase transition line of first order phase transitions, which is distinct from that line separating liquids from their vapors. That line ends in a critical point, essentially because I can continuously change the density from something reflective of a liquid to something reflective of a vapor, while I can't do that analogously for a liquid going to its crystal. I either have translational symmetry or I don't. There's nothing really in between. So rather than talk about other sorts of phase transitions, what we're going to do in the remaining lectures of the class is just to develop some ideas to help us understand the property of liquids. Now, liquids are complicated because they certainly are interacting. It's hard to neglect their interactions in a way that we can for a vapor, but they don't interact so strongly such that entropy is not important like it is for a crystal. A crystal, we can essentially understand everything by Taylor expanding its potential around some minimum value that works very well for low temperature, where there aren't large excursions, large configurational entropic effects that determine their properties. That is exactly what happens for a liquid. Liquid is a precarious state of matter in which both entropy and energy are important. So that's some foreshadowing as to why liquids are difficult to consider and why we really relegate them to more advanced classes. Okay, so a liquid. So we have a working definition of a liquid given we've prescribed these order parameters. A liquid is a phase of matter that is dense, denser than a vapor, but lacks long-range order. It has complete rotational and translational symmetry. So if I was going to look at a little piece of a liquid, what would I see? Ooh, I can make these really uniform. I would see, say, for a very simple liquid that has no internal structure, a packing of something like spheres, maybe like so. Some of them would be close together, nearly touching. Pauli exclusion principle would keep them from exactly overlapping, as would their positively charged nucleus. And it's disordered, maybe something like that. Let's denote the center of one of those spheres. With the position R sub I. That's the location of the ith particle. So when I say simple liquid, this is the kind of picture I have in mind, something that's structureless, takes up space, is close together, and lacks long-range order. Now those particles interact with each other through some potential. Let's denote that potential U. It depends on where all the particles are at one time. Let's denote those total locations as R superscript N. And what I mean by that is just some big vector of R1, R2, all the way up to Rn. Now, we've made a big to-do already that a liquid lacks long-range order. If I know where one of these particles is, say particle I don't necessarily know where a particle far away from it is in the way that I would for a crystal. If I know where a couple of the atoms are in a crystal, I can define its unit cell. I can translate that unit cell, if it's a perfect crystal, throughout all space. That does not necessarily mean that a liquid lacks structure completely. So a reasonable question that one could ask, even just at this kind of qualitative level, is in what sense does a liquid have structure? Let's denote the probability to see a specific pattern in a classical system where I can pin down all the particles as P of Rn. That would be the probability of seeing all the particles in a very specific position in space, and we know what that is. That's just given by its Boltzmann factor. In fact, it's given by its Boltzmann factor incorporating only the potential, because we know that in a classical system, kinetic energies factorize in the total energy from potential energies, therefore rendering the positional degrees of freedom statistically independent from the momentum degrees of freedom. So I can, in some sense, already solve a question we might have, which is what's the probability of seeing a specific pattern in a liquid? That's just a Boltzmann factor. But that really has way too much information than I would really care to know. I don't really care about one particle over another. I want, if I want to know something about the structure of a fluid, I don't really care so much where every single particle is, but rather some measure of how particles in aggregate, what their structure kind of in aggregate looks like. So this is the probability in the full R to the N space. We could try to go down all the way to a one particle quantity. We could ask a question, what's the probability to see a specific particle at a specific point in space? Let's denote that some little p of r vector. Well, how can we write that down? So a way to denote probabilities is to introduce a binary variable that we average. We've seen that in a number of cases. So when we thought about our Fermi-Dirac or Bose-Einstein Fermi-Dirac distributions, we could think about the occupancy of an energy level as take an expectation value over an indicator variable that tells me whether or not that that energy level was occupied or not. Anytime I have a binary variable and I average it, it has an interpretation as a probability. So a way to denote an indicator function of a continuous variable is to introduce a Dirac delta function. So if I take an average over a thermal ensemble of a Dirac delta function, that's equal to 1 if, in this case, the ith particle is exactly at the position I've specified, r. It's equal to 0 otherwise. So as I evolve a system, I count a bunch of ones. When that particle overlaps with that specific position, zeros otherwise. If I average that, it will tell me the fraction of time that particle overlaps with that position, which is then just the probability that it is found there. If you rather a graphical function of the delta function, it has infinite height and infinitesimal width, such that its integral is normalized to 1. Well, if I put a particle in a box, that box is macroscopic, so I can't really tell that there are interfaces. The likelihood of finding a particle at one point in space should probably be the same as the probability of finding it in another part of space. In fact, we've invoked such notions many times over in this class. Back when we thought about the gas in the room, the likelihood of finding a particle, a gas molecule in one corner, is equal to it being in another corner or in the middle of the room. If all spaces are equally likely, then the probability of finding it at a particular space is just 1 over the total number of places, or 1 by v. So while asking for where all the particles are at one point in time contains way too much information, asking for where one particle is contains no information, just tells us how big the box is that we've put these particles in. So we'll need to be a little more clever, but before we do, this probability of finding a particle at a specific position is very closely related to a microscopic definition of the density. Or just a measure of where all the particles are in space. Specifically, I can define a density instantaneous location of where all the particles are, rho of R, as a sum from I equals 1 to n of delta functions that in some region of space give me 1 if those particles are there and 0 otherwise. If I average this density, I can bring the average inside that sum. So I'll have a sum over all the particles, the average of this delta function. If all the particles are the same, that's just n times that average. We've just defined that average as 1 over the volume. So what I've just found is that indeed on average, this microscopic notion of the density is coincident with the bulk density. Outside its average, however, it contains a load of information. And in fact, it's an incredibly wildly fluctuating quantity. It's got delta, it's a sum of delta functions of infinite height if particles are in those positions. But as particles wander around over the course of thermal fluctuations, their average properties, at least at the single average level, lose all of that structural information. This is a reflection of this translational symmetry that a fluid has. So if the mean doesn't contain any information due to a symmetry that the system has, maybe we can look at the next order. It's the kind of game we played back when we thought about the Maxwell-Boltzmann distribution. Due to the time reversal symmetry of equilibrium, velocities on average are 0. We can nevertheless get some sense of typical velocities by looking at the variance of the velocity and taking the square root. We can ask the same sort of question in the context of densities. While the density on average of a liquid contains no real information, it's just a number, contains no structural information. If we look at something like the microscopic density squared, we might be able to encode some structural information in it. In fact, what we'll find is that this is essentially a density-density correlation function. Much like the spin correlation function we uncovered in the Ising model. So what would this look like? Let's take an average of the delta function of particles, say 1, being at R, and particle 2 being at R prime. So it's an average of 2 delta functions. That's manipulated a little bit. Let's multiply top and bottom by the probability of finding particle 1 at position R. So that's just rewriting it, multiplying by 1. But now we have an interpretation of what this means. So the left-hand side, measuring delta functions, again, have interpretations as probability. This is the probability to see particle 1 at R. And at the same time, finding particle 2 at R prime. That is equal to, this factor over here is the, if we read it in words, the numerator says the probability finding particle 1 at R and at the same time particle 2 at R prime, divided by the probability finding particle 1 at R. That's a joint probability divided by a so-called marginal probability of just one of the components. That is what's known as a conditional probability. Let's take a little bit of an aside to talk about conditional probabilities. If I have the probability of A comma B, what I mean by that is the probability of seeing A and B simultaneously. It doesn't necessarily mean simultaneous in the temporal sense, but that's seeing two random events having a given outcome at the same time. It's the probability of flipping two coins and seeing them both be heads, for example. A bar B denotes the probability of A given B. That's a conditional probability. Given I just flipped a coin and saw a head, what is the probability that if I flip another coin, I also get a head? Given I don't know, ran a 5-minute mile, what is the probability I can also pole vault? That's maybe not a very good analogy, but there is some correlation likely there between being able to run fast and jump far. That's what's encoded in a conditional probability, A bar B. A way to write that joint probability of A comma B is to take the probability of A given B and multiply by the probability of B. So the probability of seeing A and B at the same time is equal to the probability of B times the probability of A given B. Rearranging the probability of A given B, the conditional probability of seeing A given I just saw B, is equal to the joint probability of A and B divided by the probability of just B. So-called marginal probability. This is known as Bayes' theorem. So that's what conditional probabilities mean. It really means the probability of seeing one event given, you just saw another event, and is always equal to a joint probability divided by its marginal. And that's what we've just found here. The joint probability of seeing particle 1 at R and particle 2 at R prime is equal to the probability of seeing R1 at R times the conditional probability of seeing R2 at R prime given R1 was at R. So let's consider that quantity in a little more detail. So that quantity is the conditional probability of seeing, oops, got that all backwards, let's try again, of seeing, R2 at R prime, given we find R1 at R. Now, the translational invariance of our liquid means that R1 is equally likely to be anywhere. In our volume. So let's place it at the origin for simplicity. Therefore, this conditional probability is given R1 is at the origin, what is the probability that we find R2 at R prime? Let's adopt some notation that simplifies this. This is the probability to find R2 at R prime conditioned or given R1 is at 0. That little subscript there reminds us that the average is conditioned on something, in this case, conditioned on R1 being at the origin. Now, if all the particles are identical, so we're thinking about this simple fluid, I can write this conditional probability on average as a sum over all the particles j not equal to I, not equal to particle 1, divided by the number of particles there are. And if n is large, it doesn't really matter if I have divided by 1, divided by n, or n minus 1. It's just a complicated way of multiplying by 1. Now look at that. We've summed over nearly all the particles. Average delta function, factor of 1 over n out in front. This is then 1 over n times the density of particles at R prime, given R1 is at the origin. Now, this is something which is not just n over v. So unlike before, when we computed the average density, translational invariance meant that because a particle was equally likely to be anywhere, the average density didn't contain any structural information. In this case, we've broke translational invariance by putting a particle at the origin. And so averaging this density encodes some structure. For example, we can't put another particle at the origin, so that function has to be 0 there. Maybe really far away from the origin, it goes back to just the density. But in principle, it could have some complex structure. So let's define this quantity, rho times the G of R, as this conditioned density. So that's going to be N times the conditioned average of finding R2 at R. So the G of R, we will call the radial distribution function. It is the simplest quantity that encodes the structure of a fluid through the use of this density-density correlation function. By conditioning, we break translational symmetry and therefore can generate correlations. We can generate structure. It is nothing but the factors of n times the conditioned probability of finding a particle at some location in space, given I put a particle at the origin. If this system was completely uncorrelated, if I could average the positions of particles separately, I would get back, I could separate that average in the numerator, average them by themselves. The first term in the numerator would cancel out the denominator. I would get then n times the average of the delta function r minus r2. That delta function gives me back 1 over v times a factor of n, would just give me rho. Implying that if the system is uncorrelated, this G of R equals 1. So to the extent it is not 1, we are learning about the correlations in a fluid. Okay, so what does this G of R look like? Note, I've done something a little sneaky. I've defined that function as magnitude R, not vector R. That's, of course, because the probability of finding a particle some distance away from the origin shouldn't depend on the orientation of that vector due to the rotational symmetry of the system. Okay, so let's think about this. Let's start considering the G of R in a system that actually does have broken rotational and translational symmetry, but is easy to think through. Let's consider a two-dimensional crystal. So those particles are going to pack in some ordered arrangement, maybe like so. Maybe in a simple fluid, it might pack in a hexagonal lattice. Let's denote the size of the particles with the diameter sigma. And let's put the origin right here. So if I was going to look at the G of R as a function of just the magnitude R, of course, in a crystal, it will depend on the vector, but let's just radially average it. So if I look out, if this is a perfect crystal, there is a distance, sigma, where I find particles. And so I will have a peak. I will have nothing, given that particle tagged at the origin excludes some volume until sigma away, in which case I will find particles. Next, I'll go out, not find anything, until I get a second nearest neighbor, which geometrically you could work out would be at square root of 3 times sigma. Then I could look at next nearest neighbors, which are 2 sigma away. And again, nothing in between. And this pattern would go on and on and on forever. This would be at some really low temperature where particles don't even oscillate around some potential minima. At finite temperature, we would expect to see the peaks broaden a little bit. Now they are moving around. I don't find their origins always at exactly the same place. And so rather than delta functions, I would find peaks. Try this one more time. Like so. Okay, so that's a crystal. What about an ideal gas? That's another reference system we've thought a lot about. What would the G of R look like for an ideal gas? Well, does an ideal gas have any structure? No, in fact, we imagine in an ideal gas, a particle takes up no space. So in fact, they are uncorrelated. So that G of R should be flat and set to just 1. Uncorrelated particles have no modulation in this function, the G of R. Now, is this really possible? Is it possible to have a G of R that starts at 1, even at R is really, really small? No, that would be saying that there is a finite probability to find 2 particles on top of each other, which we know can happen. So what would be maybe a more realistic G of R for a gas? Well, to work that out, let's consider 2 particles interacting weakly through some potential. And let's define that potential as U2, depends on R. For something like argon, something simple. So what might a potential for two argon atoms look like? Well, at distances smaller than their diameters, those particles, argon atoms, are going to exclude volume. So that potential should rise up. At large distances, how do argon atoms interact? Through attractive dispersive interactions. So ooh, that's terrible. Let's try that again. So maybe a reasonable model of a potential for something like argon atoms would look like this. You'd have some excluded volume here. And some dispersion that is attractive there. Now, excluded volume, probably more likely than not, is going to go exponentially due to wave function overlap. Dispersion, you know how it goes like 1 over r to the 6. And importantly, as r goes to infinity, u2 of r will go to 0. If I just have two particles in the world, what is the probability of finding two particles a distance r apart? Well, it's going to be just proportional to that Boltzmann factor. And as r goes to infinity, the potential goes to 0. So P of r will go to something like 1, or the density will go to something like 1. So ignoring many particle effects, which is reasonable if the density is low, we might expect that the G of r goes like just this Boltzmann factor. Indeed, if we were to then draw that, at really short distances, the potential is large and positive. E to the minus a large and positive number is small. So we would find, that's a little tilty, something that starts at a small value, then is peaked, and then plateaus to 1. All right, so that's a reasonable model for a gas of something like argon. All right, now we've gotten some intuition for what these G of R's look like. Let's take a leap and imagine what it might look like for a liquid. For something, again, simple and structureless. And if we were going to draw what a snapshot of a fluid might look like. We did this at the outset, maybe something like this. If I tagged a particle at the origin and looked at concentric circles around it, oof, I don't know why I did that. I would find intersections, again, where there's distances where there is an enhancement in the likelihood that a particle is there, and distances where it's suppressed. It's not as extreme as it would be in a crystal, however. So a typical G of R, if I go really far away, particles should become uncorrelated. So it should go to 1. If I look really close, there's no probability of finding a particle on top of another particle. And the correlation is likely strongest near that first peak. And for a simple model like argon, we'll have a few layers before that correlation goes away. How high is that first peak? Well, if I ask for the number of particles on average between two distances, say RA and RB, from a tagged particle, let's denote that number N between RA and RB. Let's do it as a function of some intermediate R. The number of those particles is just going to be given by summing up the density over that domain, given that there's that particle at the origin. In 2D, I can average over orientations of that vector, get a factor of 2 pi, and a r dr. The density given a particle at the origin is rho times the G of R. If I integrate that from, say, something like RA is 0 to RA is something like 3 sigma over 2. RB is 3 sigma over 2. So integrating over this first peak, but in 2D. Oof, that's really too big. The width is essentially given by sigma. If I know the area, I can infer something about the height. In 2D, this turns out to be about 6. And you can kind of even get that from this picture. Just drew this haphazardly. Whoop, that particle at the origin has 1, 2, 3, 4, 5, between 6 and 7, depending on exactly whether or not this particle here or here was really there or not. That was just drawn on a whim. You yourself could try to draw a bunch of spheres of the same size around a central particle, and you'll find that If you make them somewhat disordered, it will be quite close to 6. If you extend that rationale to 3 dimensions, you now have a factor of 4 pi. You have an integral of RA from 0 to RB, say 3 sigma over 2, R dr squared, rho times the G of R. This is pretty close to 12. Indeed, locally, just due to packing, simple liquids will look a lot like the crystals that they will form under, say, cooler conditions. It's only as you build up density further and further away that you start noticing that those correlations don't persist ad infinitum, but decay, leaving you something without long-range order. All right, what about for something like water? A not so simple liquid. What would its G of R look like? Well, water we know forms hydrogen bonds, like so maybe. Those hydrogens interact with the oxygens of other water molecules. How many hydrogen bonds are formed with one water molecule at the center? 4, right? So the coordination number of something like water, liquid water, is much lower than a simple fluid in 3 dimensions. Additionally, if I was going to carry on this hydrogen bonding pattern, we know essentially what these angles are like. The next nearest neighbor, if I was looking at the oxygen-oxygen radial distribution function, is not at 2 sigma, but actually a little closer together. So if I was going to draw the G of R for something like water, so first, what is typical diameter for water? Anyone know? It's pretty close to 3 angstroms. Going to have a height that will integrate up to something like 4. But rather than the nearest neighbor second layering being at 6 angstroms, there's a peak at a distance that corresponds roughly to the tetrahedral angles that those hydrogen bonds form. Turns out to be about 4.5 angstroms. All right, so we've uncovered a means of characterizing the structure of a fluid. We've noticed that it's insufficient to just ask where particles are, where a particle is in space. It's too much information to ask where all the particles are in space. So we found a happy medium by codifying the structure in this radial distribution function by asking the conditioned question, given I put a particle somewhere, how does that affect the density away from it? And now we've gotten some intuition for what such quantities look like. We will find in the next lecture that we can use the G of R as a means of relating structure to thermodynamics. So if we know the G of R in some cases, we will know average properties of a system, like what its pressure is or what its energy is. And from there, and therefore making approximations to the G of R, we can derive approximate equations of state and the like. Okay, so that's all for the last week. So stay tuned from that. Hope you all have a happy break and Thanksgiving, and I'll look forward to seeing you in the live session.